these vectors are used, they look like line segments. And as a matter of fact, you can call them a directed line segment. So I've added that there, also known as directed line segment. And they are expressed in a couple of ways. Now we're going to be looking at them geometrically and algebraically. But here are the same. It's the same vector shown here. If it's in polar coordinates, then that means you will put the radius and then the angle. And that's a polar coordinate. I like polar coordinates because it doesn't tell, this is what it does horizontally, this is what it does vertically. It says, hey, it starts here and it goes in this direction, because it may be a really odd direction. So those are polar coordinates. It shows the distance from any point. Now, if it's on the Cartesian plane, it is expressed, as these V's that are oriented kind of like that. And the x-coordinate tells the horizontal, what it does horizontally, and then what it does vertically. So, which makes sense. It just, you can tell it's directed line segment because of this notation with this thing. That's called component form, which we'll be using that for a couple of days. And let me show you an example. And I'd like you to write this example down because I'm going to put a lot of information on it. So let's say that you have this, and I'm going to call this vector A. So put an A with a little weird ray on top of it. I'm going to call this vector K. Now I can call it CD and do this. CD with that little ray. And that's the same thing as lowercase a. So they're the same thing. You can name it for its endpoints. And please know that this does not mean, hey, the direction is going this way. It's saying the force is going this way. And its beginning point is 0, 0. And its end point here is 7, -4. So to write it in component form, as I wrote up at the top, component form a few seconds ago, from the beginning, it goes positive 7 units, and it goes down 4. So you would write it like that. And this is what it looks like in component form. Now notice this one does not begin at the origin. When they begin at the origin, they're said to be in standard form. This one begins here and goes there. So if I'm writing this one in component form, let's look. Horizontally, it goes from -2 to -7. That's a loss of 5. Yes? Vertically, it goes from 4 down to -2. So since it goes down, it's -6. So here's a component form of K. But let's say that I want the magnitude. If you want the magnitude, here's how you have to look at it. So the magnitude of A, I'm going to do double bars, A. And I have those notes written above. I'm going to show you that in a second. So if I'm trying to find this, I make a right angle with the horizontal axis, and I say, okay, this is 7, and this is 4. It's actually -4, but when I square it, it won't matter. So I'm just going to use a distance formula to find out what the magnitude is of this. And the magnitude of this is equal to 7 squared, which is 49, a squared plus b squared, plus 16, which is the square root of 65. So notice that my distance is my magnitude. On this one, I would do the same thing. I pretend like there's a little right triangle here, and I say, okay, so it went down 6, it went over 5. It matters not that it was negative when I'm doing magnitude, because your magnitude is going to be positive no matter what. It's distance. So 5 squared is 25. 6 squared is 36. So I think that's square root of 61, which is my magnitude of vector K. And here are the notes on what I just did, everything I did. And I want to show you something else. Please look at these vectors right here. Let me make that a little bit bigger. Oh, that didn't work. Okay. on this, you will notice that they all go in the same direction, but are they equivalent? Now the checking for equivalence, they must be not only in the same direction, and I mean the arrows have to be going the same way. If on this one the arrow is going the other way, it would not be equivalent. They have to be in this exact same direction and the exact same magnitude. Now I'm not going to try to do that on this because I can't see what the points are, but I'm saying the coordinates. But if they're equivalent, that means I could take AB and set it right on top of CD and it would be a perfect match, and so on and so forth. So please know that when you're comparing two vectors, they have to be the same magnitude and the same direction. So if you will pause and try these 3 examples, I'm going to post the answers in just a second. I am going to write them down in 3, 2, 1. Okay, so if you do the first one right, since it started at 0, 0 and went here, there it is in component form. And its magnitude is simply how far it went. 7 squared is 49, 2 squared is 4, and the square root of that. Answer is 53, that sum. Same thing here. It goes from -1 to 3, it means it went to the positive 4. From -1 to 5 is to the positive 6. And 16 and 36 is 52. But 52 can be simplified to 2 root 13. Now, to check for equivalence here, all of these had the same distance. They all had the distance of 9 plus 4, I should do that, which is the square root of 13. And they all pointed the same direction and had the same slope. So the slope being 3 over 2. Now, we rarely talk about magnitude or direction, as slope. So I'll be showing you tomorrow how to express this as an angle using trig functions. But I need to show you one more thing. Let's say that I want to multiply, I'll start with adding. Okay, if I was told to add those original 2 vectors that we started with, to add vector A to vector K. In order to do that, what I do is I can start either way, right? I'm going to start 0, 0 to here. At this point, I'm going to add K to it. But K, remember, so from this point, K goes back 5, 1, 2, 3, 4, 5, horizontally, and down 6, 1, 2, 3, 4, 5, 6. So it appears this would be my endpoint, which is 2, 6, 8, -10. So here is the total where it comes out at if I were to add A to K. Now personally, I think it's a lot simpler to add them in component form, because if I had 7, -4, and I was adding -5, -6, I find it much easier to think of it algebraically. 7 plus -5, I'm adding those, is 2. -4 plus -6 is in fact -10. So you can do it geometrically, or you can do it algebraically. If it said to do 2 times A, then I would it's this ray twice. Again, you can do it geometrically, or I can just take this and multiply it by the scalar of 2. And that would be, if it works, it'll be 14 -8 is where I'll end up at. My total vector will be 14 -8 if I double it. And I'm referring to this one right here. So that's how you work on these algebraically. If I were subtracting, and I hate the subtracting. So let me show you what happens if I take A minus vector K. Algebraically, I just subtracted and I got 12, 2. That was super simple. But if I actually wanted to work, I don't know if I can pick this thing up. I would have to pick this up, and I would have to put it head to head over here. So if I just simply, I can't get it, picked up the AB and put it over here, 2, 3, 4, it would look like this. You put them, the terminating point to the terminating point, and see where you end up here. And it's 12, 2. So see how it's so much easier trying to think how to put those together and where it would land. It's just easier to do that algebraically. So that's how you subtract. Okay, I'm going to go back to that original screen. Make sure you can get all your notes. Again, we'll be working with this polar coordinate one later on in the week, and you guys take care.